right, so what happens when you have a function that is in terms of y instead of in terms of x? For example, the function that we have here is x squared, or x equals y squared minus 3. So if we wanted this in terms of x, we'd have to, add 3 to both sides and take the square root, and it would actually be a really gnarly looking function, right? And then we'd have to have the positive and the negative. And the issue that we would have is, let's just draw this, okay? So we're going to find the region bounded by x equals y squared minus 3 and y equals x plus 1. So first we're going to draw x equals y squared minus 3. Now think about, this is an inverse of a function we know very well. So x squared minus 3 we know very well. It's a parabola that's shifted down 3. So the inverse of that would be, we switch the x and y, therefore we reflect it about the line y equals x, but so it flips and it shifts left 3. So this parabola shifts left 3 and looks something like that. Oh, it's rounder than I thought. Okay, so there's our parabola right there. And then it's also bound by the line y equals x plus 1. So that is this line right here. So now here's our dilemma. If we were to do this the way that we have learned to do this before, we would think, okay, top curve minus bottom curve. I'm trying to get this line to be straight, but you know me in drawing straight lines. I'm not great at it. Okay. So, we would say top curve minus bottom curve, right? But we have a little bit of a problem because in some places, the top curve is different than in other places. In fact, like right here, this is on top, right? But then when we come here, what curve is the top and what curve is the bottom? And even if we did figure out what the top and the bottom was, is the area under that curve in between these curves, like, oops, I don't want to erase that. Like if this is the top curve and that's the bottom curve and we found that area, is that really a part of the area that's found in this curve? Not really, right? And so we have this kind of dilemma because there really, in some places, isn't a top curve and there really isn't a bottom curve. And so because this is in terms of y, the cool thing is we can actually just take the integral in terms of y. And so instead of our boxes going this way, right, instead of our scanner kind of going this way, because our issue would be then when we get to here, our scanner isn't touching both of our curves, it's only touching one. Instead of our boxes going that way, what we're going to do is we're going to have our boxes going this way. See how my scan gun is still touching the top. It's touching the top curve and the bottom is touching the bottom curve. And it still is, as it moves, if you can imagine this moving, if I was really good at like making animations, I would have totally like made a cool animation for this, but probably could have found one. Anyway, so imagine this, here's our scan gun, beep, 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 right? It's moving. It's touching the top curve. The top is touching one curve and the bottom is touching the other curve. And the top is touching one curve and the bottom is touching the other curve. So it's moving along this line. And it's moving starting right here to here, right? So we're going to think about this in terms of y. So what is the width of this rectangle? Well, it's dy, right? dy is the width of the rectangle. And what's the height of the rectangle? Well, the height of the rectangle would be the right curve minus the left curve. So, and we can take the integral of this to find the area in between the curves with respect to y. So it makes it so much easier than having to put this all in terms of x. And then we have to figure out what are our bounds. Like what actual, before we had these curves that didn't intersect. So we said, we looked at these curves, it'll just take a minute, there it is. We have these curves, and they didn't intersect, so they told us in between A and B, right? But these curves create their own boundaries, right? We're going in between here and here. And so now we have to figure out how do we find those, what those actually are. And so a lot of times these ones are going to be on like a calculator portion of the test, because you're going to use your calculator to find the intersection points. However, it's very important, as it says right there in your book, you must show an equation setup even when using a calculator to find the intersections. So just because you found the calculator to find the intersections does not mean that you get to just like phone it in and not write down any of this work or any of these. Okay, so you have to show the equation setup. So the question is, what is the area that we're looking for, right? Well, we're going to find the definite integral, right, from a to b of f of x minus g of x dx, right? That's the width of the rectangle, and the height. Ha! But see, I just did it in terms of x. Guess what? Well, we're not in terms of x anymore, right? The width of our rectangle is dy. So let's just change that to dy. We're going to change this to functions of y, not functions of x. We're going to do functions of y, so gy and gx. Or gy and fy. Oh, those are hard to say. I'm not used to saying f of y. All right, so the question now is, what are the intersection points of this one? We're going to do this one without a calculator, and we're going to figure that out. So where do these two curves intersect? Well, our first curve is x equals y squared minus 3, and our second curve is y equals x plus 1. Now remember, to find where they intersect, we can just set them equal to each other. And so we're going to just go ahead and do that. We're going to make this in terms of x, so that it's y minus 1 equals x. And then everywhere there's an x in the other one, we can just replace that with y minus 1. So we have y minus 1 equals y squared minus 3. And so then we're going to go ahead and subtract y and add 1. So we're going to get 0 equals y squared minus y minus 2. So then to find where this is equal to 0, we're going to go ahead and factor that. And we get y minus 2 and y plus 1 equals 0. So therefore, these functions intersect at 2, at y equals 2, and at negative 1, because that's the zeros of those two factors. So again, to find the intersection points, you use substitution to set them equal to each other, and then you just solve for the zeros, and that gives us the intersection points. So we know that at y equals 2 and y equals negative 1, they intersect. So let's go look at our functions here, and we're going to remind ourselves that at this point right here, y equals negative 1, and then at the other point, y equals 2. So these are going to be our limits of integration, right? Because we are going, if you think about our scan gun, we're going from here, and we're just going beep, 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 and we're adding up all these infinitely small rectangles to get the area in between these two curves. So our actual integral is going to be, our area is going to equal the definite integral from negative 1 to 2 of our right curve, which is y minus 1, right? Because we use it in terms of y, right? So we want it to be an explicit equation in terms of y. So we went ahead and just did y minus 1 equals x there, okay? Y minus 1 minus our left curve, which is y squared minus 3 dy. And so let's just do a little bit of algebra here to get that looking a little prettier. We have y minus 1 minus y squared minus, or plus 3 dy. And then our area equals negative 1 to 2 of negative y squared plus y minus, plus 2 dy. And then we can go ahead and integrate that with respect to y. So, since y is our variable and we're doing dy, then that's literally all we have to do. It's just like integrating with respect to x. We just go ahead and integrate it. So we have, that would be negative y cubed over 3 plus y squared over 2 plus 2y, evaluated from negative 1 to 2. And then we're going to go ahead and evaluate that. So we're going to plug in 2. I'm going to do a different color for that one so that we can remember what we're doing. So negative 8/3 plus 4/2 plus 4 minus 1, because negative 1 cubed is negative 1, and then negative 1 is positive 1. 1/3 minus 1/2 minus 2. And because we are in calculus, we don't need to go any further than that. We could go ahead